Hi everyone, welcome to another YouTube video for Programming 2. This video is for lab number 11 and it's all about recursion. So you should have your Programming 2 lab sheet here, and we're just going to go down to exercise 4. Write a recursive method to compute Ackermann's function defined by the equation. And there is three parts to this equation. So the result of Ackermann's function is dependent on the input. So if x is equal to 0, return y plus 1. If y is equal to 0, return the Ackermann's function on x minus 1 and 1. So that's a sort of recursive call. And for any other input, you have to compute this, Ackermann's function on x minus 1, and for the second input, it's Ackermann's function on x and comma y minus 1. So it sounds like a lot of information, but actually this is really simple to do. So let's just go ahead and get started. I'll go into Java here, and let's say I want to create an Ackermann's function method, and we're going to translate the mathematics to Java so that we can compute it. So public static, we'll just make it static. We're going to return an integer, and we need as input an x integer and a y integer. So looks like that. So then we have to return something. I'm not sure what to return yet, so I'll put 0. So we would input values like that, and we would want to maybe print out the output like that. So the first case was, let's see if we can translate this into Java. So the first case is that if x is equal to 0, then return y plus 1. So that's pretty easy. This is called the base case for a recursive call. If x equal to 0, then return y plus 1. And that's it. Now there's another case. If y is equal to 0, then return Ackermann's function on x minus 1 and 1. So if y is equal to 0, return, and here's where the recursion comes in. We're calling this again, but we're reducing the values. So it's x minus 1 and 1. So x minus 1 and 1 if y is equal to 0. It's exactly what we have here. And lastly, and a little bit more complicated, these are the base cases, and now we want to get into the recursive call. We can write something like this. So for all other cases, for values of x and y, we're going to then compute this. We're going to return the Ackermann's function on x minus 1, the Ackermann's function on x and y minus 1. So that translates into Java like that, x minus 1, and then Ackermann's function on, what was it, x and y minus 1. And that's pretty much it. And don't forget, you should return that value. So that's what the code looks like. It's not very complicated. You just have to go through all the cases, and don't let the mathematical notation fool you or make it any more difficult than it needs to be. It's quite straightforward. So if we run this, that's the output, like that. Now, the thing about Ackermann's function is that even though it is very simple, it's surprisingly computation intensive. So I can compute small values like this, like 3. You see how quickly that grows in values. If I add a 4 there, it goes up very, very quickly. But if I do this, if I change this to 4, something kind of bad happens. So it's computing away, as you can see, but all of a sudden we get a Stack Overflow error. Now that's bad. But it's to be expected in this case, actually, because it grows so quickly that Java just simply does not have enough memory on the stack to actually compute it. So this is a very well-known result in computability theory, and if you're interested, you can read about it in the lab, and there's some links to some more information about it. So that's about it for this video, and hope to see you this week in the lab and the lectures. Goodbye.